Previously, we have learned how to find the derivative at a specific point and how to find the derivative as a function using the definition of a derivative. And we use that definition to help you develop the concept on what the derivative means. And if you recall, the derivative is the slope of the tangent line at a given point on the function. So now that we have learned the long way to do it, that has helped develop our foundation of understanding for derivatives, I'm going to walk you through the shortcut. So we have some rules that we can use that make finding the derivative a lot easier and a lot quicker. And so I'm going to walk you through those rules right now. Okay, so the first rule is called the constant rule. So if you have any function that is a constant, like f of x is equal to 3 or f of x is equal to -2, if you have a function that is a constant function, which means it's going to be a horizontal line, the derivative is just automatically 0. It doesn't matter what point you're looking at on the graph of the function, the slope of a horizontal line anywhere is going to be 0. So if we look at, for example, we're using, in our first example, f of x is equal to 8. If I have the horizontal line, f of x is equal to 8, here's my line. At any point on this line, if I find the tangent line, at that point, the slope of the tangent line is going to be 0. So I would write down the derivative of f is 0. Now you can also write it using this notation as well, where I could write the derivative of 8 is equal to 0. So that's our first rule. Our next rule, which is truly the most handy, is called the power rule. So if you have a function in this form, where it's f of x is equal to x to some power. So for example, f of x is equal to x squared or x to the 5th or something of that nature. Then all you're going to do, rather than try to find the limit and go through the whole definition of a derivative, all you're going to do is you're going to take whatever the value is of your exponent, in this case it would be n, and you would bring it down in front. So your n would come down in front, and then you decrease your exponent by 1. So you can write it using the f prime notation or the d dx notation. So you pull your exponent down in front, and then you decrease your exponent by 1. So applying it to this example right here, if I want to find the derivative of x to the 10th, the shortcut would be to bring that exponent down in front, multiply it by x, and then raise the exponent by 1 less. So that would be 9. The next example, if I wanted to find the derivative of g, so g prime would be, I would take the 2 down in front. Now if there's something already in front, you just multiply it. So I would take the 2 times the 3, that would give me a 6. And then I have x to the 1st because I decrease my exponent by 1. Now the next example, we have more than one term. You can combine the rules and take the derivative of each term separately if each term is differentiable. So in this case it is. We know that constants are differentiable, and we have 2x to the 5th. We can use a power rule on that. So if I wanted to take the derivative of f, I just take the derivative of each term separately. So I bring the 5 down in front, which would give me a 10. Then I have x to the 4th because I decrease my exponent by 1. And then when I take the derivative of 7, that's just a constant, so that would be 0. And you don't have to write the 0 in there. You can just leave it as 10x to the 4th, which is totally fine. Okay, so now we're going to practice finding the equation of a tangent line like we did in the previous section. However, now we're going to use the shortcut, so it's going to make it a lot easier. So we need to find the equation of the tangent line to the graph of f of x is equal to x squared minus 4x plus 6, and we want to find the tangent line at x equals 1. So we're looking for that point right there, whatever that tangent line is for that point. So we want to find an equation in this form. I know that the m of the tangent line is going to be the derivative at that point. So I'm going to find the derivative at 1. Well, now I can find the derivative a lot easier. If I use the shortcut that I just found, the derivative is going to be, if I look at the x squared first, that's going to be 2x. I bring the 2 down in front and then decrease my exponent by 1. Minus 4x is going to become minus 4 because this exponent here is 1. So when I bring it down in front and multiply it by negative 4, I get negative 4. And then when I decrease the exponent by 1, I get x to the 0. But we know that x to the 0 is just 1. So we don't need to put in that x to the 0, but we can if we want. We just know that x to the 0 is 1. When I take the derivative of the 6, that's constant, so that becomes 0. And again, you can write in the plus 0 if you want, but you don't have to. So the derivative at any point on this graph is 2x minus 4. If I want to find the derivative specifically at 1, I need to plug in 1 to the derivative. So I get 2 times 1, which is 2. And then 2 minus 4 is a negative 2. So now I know what my slope is. So I'm going to plug in negative 2 for my slope. But now I have to plug in a point for x and y so I can find b. I know I definitely want to use the point 1 for x because I know for sure that that's on my tangent line. If I plug in 1 for x, I'm going to get out 3 for y. So I know my corresponding value of y is 3. So now when I solve for b, I'm going to find that b is 5. So my tangent line at x equals 1 is going to be y equals negative 2x plus 5. And we can draw it on here just as a quick check. If my y-intercept is 5, and I go down 2 and over 1, so down 2 over 1, down 2 over 1. So here are all my points. And if I have a nice steady hand, I can draw that tangent line. The next rule we're going to talk about is called the product rule. And this is applied to a function in which there are 2 other functions being multiplied together to form that function that we're trying to take the derivative of. So we're going to say let f of x and g of x be differentiable functions. If they're each separately differentiable, when I take the derivative of the product, I'm allowed to use this quick shortcut. So in the shortcut says, if I want to take the derivative of them multiplied together, then what I'm going to do is I'm going to take the derivative of one of them and multiply it by the second. And then I'm going to take the derivative of the second and multiply it by the first, and then add them together. Here is the notation using the prime notation. This is my preference of looking at the product rule. I think it's less messy and easier to read. So this prime notation is what I'm going to use. Okay, so in this first example, we have a function called j of x, And j of x is made up of the product of two functions, f of x and g of x. We want to find the derivative of j of x. Because j of x is made up of a product of f of x and g of x, we're going to use the product rule to find the derivative of j at a specific point 2. So to find the derivative of j of x, we're going to use the product rule. And the product rule says I take the derivative of one of them, so we'll start with f, and we multiply it by the second one. And then we add it to the derivative of the second times the first. Now, I want to evaluate this at x equals 2. So I'm going to plug in 2 everywhere I see x. So I have f prime of 2 times g of 2 plus g prime of 2 times f of 2. If you haven't already noticed, I'm a very visual person and I like using colors. Hopefully that helps. Now, all of this information was given to us in the problem. We don't know what the functions actually are. Like, I don't know if f of x is x squared or g of x is, x cubed. We don't know what the functions actually are. But if we're given the right information, we don't need to know that. So here's all the information that's given to us. I know that f of 2 is 3. So I'm going to plug that in here. F of 2 is 3. We're given that the derivative of f at 2 is -4, so that's going to go here. We're given that g of 2 is equal to 1, so that's going to go here. And then we're given that g prime of 2 is 6, so that's going to go here. And so we're going to, when we multiply this together, we're going to get -4 plus 18, which is going to give us a final answer of 14. So using the correct notation, I could write this, that 14 is equal to j prime of 2, or the derivative of j at 2. Now I'm going to apply this to a function that we actually know what the formula is for that function, but we're also not going to evaluate it at a specific point. So once we figure out what the derivative is, we're not going to plug in any values of x. Because it just says to find the derivative, it doesn't have a value plugged in for x. So what I want you to do is imagine, and again, I like using colors because it helps me think. I'm going to identify this as f of x, and I'll identify this as my g of x. If we use the product rule, because I have a function j of x that is made up of two functions being multiplied together. So if I use the product rule, that means I'm going to take the first function and find the derivative, and then multiply it by the second function, and then I'm going to add that to the derivative of the second function times the first function. And then off to the side, we can do a little scratch work. If I want to find the derivative of f of x, we said f of x is x squared plus 2. F prime of x is going to be, using our shortcuts, I bring the 2 down in front and I decrease the exponent by 1. So that makes it 2x to the first. And when I take the derivative of a constant, which is 2, it's just 0. So my derivative of f of x is going to be 2x. Now, if I do the same with g of x, we said g of x was 3x to the third minus 5x. using the same rule, that combination of power rule, constant rule, all those shortcuts we have, I'm going to bring the 3, the exponent, down in front. And since I already have a number down in front, I'm going to multiply. So that's going to give me 9x, and then I decrease my exponent by 1. So that gives me 2. And then for the second term, I have an exponent that's 1. So when I bring the 1 down in front, I get 1 times -5 is -5. And then that gives me x to the 0 power, which is just 1. So I don't need to put it in there, but I can if I want to. Okay, so now we have all the pieces, and we can plug this in. So f prime of x, we said was 2x. G of x, we said was 3x to the 3rd minus 5x. We're going to add g prime, which is 9x squared minus 5, and multiply that by f of x, which we said was x squared plus 2. So to simplify this, we're just going to multiply everything out. Now, I feel fairly confident that at this point, you guys can FOIL and combine like terms. So I'm not going to go through these steps. I'll just tell you that when you write down the final answer and you FOIL and combine like terms, you should get 15x to the 4th plus 3x squared and then minus 10. So that will be your derivative after you clean up this step right here. Okay, the next example, we have 2x to the 5th times 4x squared plus x. So we have an f of x that is written as the product of 2 other functions. So we'll say g of x is the 2x to the 5th. And we'll have, let's use h of x as our second function. And we'll call that the 4x squared plus x. So to find our derivative of f of x, we need to use the product rule. So we're going to take the derivative of g of x times h of x, and we're going to add that to g of x times the derivative of h of x. Off to the side, we can do some scratch work. I'm going to find the derivative of g of x using our shortcuts. So that's going to be 10x to the 4th. And our derivative of h of x using our shortcut is going to be 8x plus 1. So now I can go ahead and plug in all that information. So I have g prime of x, which is 10x to the 4th times h of x, which is 4x squared plus x. And we're going to add that to g of x, which is 2x to the 5th, and multiply that by h prime of x, which is 8x plus 1. Then when we multiply that all together, we're going to get 56x to the 6th. Now we're going to go over the quotient rule. And the quotient rule is similar to the product rule and how you're going to use it. It just has a different formula. Here's one way to use the notation for the quotient rule. This is my preference. I'm going to use this notation. So the quotient rule says if you have a function that's defined by taking one function divided by another function, to find the derivative, then you take the derivative of the numerator function, multiply it by the denominator function, then you subtract the derivative of the denominator function times the numerator function, And then you take that whole thing and divide by the denominator function and square it. Now here, the order really matters because we're dealing with division and subtraction. So in the product rule, it really didn't matter. For example, if I wrote it as f prime g plus g prime f, or if I wrote it as g prime f plus f prime g, because multiplication and addition is commutative, right? I can switch the order and it doesn't matter, right? 3 times 4 is the same as 4 times 3, and 3 plus 4 is the same as 4 plus 3. So the order didn't matter so much with the product rule, but with the quotient rule, you really have to pay attention and make sure you're doing it in the correct order. We're going to use the quotient rule in this first example to find the derivative of k of x, which is 5x squared over 4x plus 3. I'm going to let f of x be my 5x squared, and I'm going to let g of x be the denominator function, which is 4x plus 3. So to find the derivative using the quotient rule, I need to take the derivative of f of x, which is the derivative of the numerator function. It's important that you get the order correct in this case. Okay, and then I multiply it by the denominator function, and then I subtract the derivative of the denominator function times the numerator function, which is f of x, and then I take the denominator function and I square it. And then of course you simplify it if you can. So I'm going to go ahead and put all this in now. The derivative of f of x using our shortcut is going to be 10x. And then I'm going to multiply that by g of x, which is 4x plus 3. Then I'm going to subtract the derivative of g of x, which would be just 4, times f of x, which is 5x squared. And then I'm going to divide by g of x squared. So I'm going to put in parentheses down here 4x plus 3 squared. When you clean all of this up, what you're going to end up getting is 20x squared plus 30x all over 4x plus 3 squared. Okay, let's do another example just to practice. I have another function where it's the quotient of two other functions. So I'm going to let f of x be the numerator function, which is 3x plus 1. And I'm going to let g of x be the function in the denominator, which is 4x minus 3. So to find the derivative of h of x, I'm going to use the quotient rule. And I always want to make sure that I take the derivative of the numerator first, because order matters with the quotient rule. So I'm going to take the derivative of f of x times g of x, and I'm going to subtract the derivative of g of x times f of x, and then I'm going to divide by the denominator function squared. Okay, when I fill in these values, since f of x is 3x plus 1, when I find the derivative, I'm just going to have 3. And then I'm going to multiply that by g of x, which is 4x minus 3. I'm going to subtract and take the derivative of g of x, which is just 4. And I'm going to multiply that by f of x, which is 3x plus 1. And then I'm going to divide that, and in the numerator, I'm going to take 4x minus 3, which is my g of x, and square it. When I simplify all of this, I'm going to get negative 13 over 4x minus 3 squared. In these next two examples, I'm going to show you how there are times that you have a choice between using the quotient rule or the power rule, and even the product rule. So there isn't always just one way to do something. A lot of times there are different ways that you can take the derivative. And so in this first example here, I'm going to show you how we can use the power rule, or we can use the quotient rule, and we'll get the same answer. So I want to take the derivative of x to the negative 4. If I use the power rule, and I take the derivative of x to the power of negative 4, I pull the negative 4 down in front, I multiply by x, and then I decrease the power or the exponent by 1. So if I subtract 1 from negative 4, that's going to give me a negative 5. And then I can also write this, because I remember way back when in a college algebra class that if I have an exponent that's negative, that means I can take the reciprocal to make that exponent positive. So I can rewrite this as negative 4 over x to the 5th. So either one of these is good. They're both the answer. Now let's do this with the quotient rule. I want to take the derivative using the quotient rule. Before I take the derivative, I can actually rewrite x to the negative 4 as 1 over x to the positive 4, right? Because negative exponents means I can take the reciprocal to make the exponent positive. So now if I use the quotient rule, if I take the derivative of the top function, that's 0, times the bottom function, which is x to the 4th, and I subtract the derivative of the bottom function, which is 4x to the 3rd, and I multiply it by the top function, which is the constant function 1, and then I divide this by the bottom function squared. So that's going to give me x to the 4th squared. Okay, now when I clean this up, 0 times x to the 4th disappears. And I'm left with negative 4x to the 3rd over x to the 8th, because when I raise a power to a power, I have x to the 4th squared, I multiply the exponents. So that gives me x to the 8th downstairs. And then when I finish simplifying this and I cross off 3 x's upstairs, 3 x's downstairs, I end up with negative 4 over x to the 5th. So this just goes to show that there's more than one way sometimes to take a derivative. And if you have a preference and you see that the expression can be manipulated in a way that you can use your preference, then go for it. Okay, so the next example, we can use the power rule and the quotient rule again. We can use the power rule. We can use the quotient rule. And we can actually use the product rule as well. And you'll see that they all come out the same. So first, if we rewrite this as 6 times x to the negative 2, we can use the power rule. If we take the derivative of 6 times x to the negative 2 using the power rule, I would take the negative 2, bring it down in front, and multiply it by the 6. So I would get negative 12x, and then decrease the exponent by 1. So I would get a negative 3. And then, of course, you can rewrite this as negative 12 over x to the third. Using the quotient rule, we would leave it as a fraction. And I would take the derivative of the top, which is a constant, so that would be 0, times the bottom function. Then I would subtract the derivative of the bottom function, which is 2x, times the top function, which is 6, all over the denominator squared. When I clean this up, I get 0 times x squared, that's 0. So I'm left with on the top negative 12x over, then on the bottom I have x to the fourth. And when I cross off what they have in common on the top and the bottom, which would be an x, I'm left with negative 12 over x to the third. So far, we have shown 2 different methods to find the derivative of the same function. If I use the product rule and I take the derivative of 6 times x to the negative 2, I can think of 6 as my f, and I can think of x to the negative 2 as my g. So I want to take the derivative of f, which is 6, and if I take the derivative of 6, that's 0, times x to the negative 2, and I want to add that to the derivative of x to the negative 2, which would be negative 2x to the negative 3, and multiply that by my f function, which is 6. So let's color code this. This is g, this is g prime, this is f prime, and this is f. So I take the derivative of f times g plus the derivative of g times f. Now, when I simplify this, 0 times x to the negative 2 disappears, and then I'm left with negative 12x to the negative 3, and I can rewrite this with positive exponents by taking my x to the negative 3 and finding the reciprocal to make my exponent positive, and again, I get this. Okay, here's some more examples of combining rules. It says for k of x equals 3 times h of x plus x squared times g of x. We're going to find the derivative of k of x. So notice here I've got a product rule, and here I've got a constant times a function. So the first term I can just take 3 times the derivative of h of x. Now, this is where we have to be careful. I have 2 functions. I have x squared and I have g of x. So I have to apply the product rule. So I'm going to do this inside the brackets. So I'm going to think of x squared as my f. And I'm going to think of g of x as my g to make it a little bit easier. And so for my product rule, I'm going to take the derivative of f times g of x and add it to the derivative of g of x times f of x. So when I bring this down, I have 3h prime of x plus, now I know what f of x is, it's x squared. I don't really know what h of x is, or h prime of x, or g of x, so I just have to leave it as is. So I'm just going to go ahead and replace f of x with x squared and f prime with 2x. Since f prime is the derivative of x squared, that's going to be 2x times g of x plus the derivative of g of x times f of x, which is x squared. So this is as simplified as we can get because we don't have any other information, but if we knew what those functions were, we would be able to. So now we're going to go through an example where you have to use the product rule more than once. And we have a function k of x that's defined by the product of three functions. We have f of x, g of x, and h of x. So we need to obviously use the product rule because we have f of x times g of x times h of x. But what we're going to do is first rename f of x times g of x. We'll come up with a different name. Let's call it m of x. I'm going to say let m of x be f of x times g of x. Then we would have that m prime of x is going to be f prime of x times g of x plus g prime of x times f of x using the product rule. I'm going to rewrite k of x now as m of x times h of x, since I substituted m of x in for f times g. And so now when I take the derivative, I'm going to use the product rule on these two. So I'm going to take m prime times h plus h prime times m. I know what m prime is, and I know what m of x is because we define m of x as f of x times g of x. And then I use the product rule to find the derivative of m of x. So now I'm going to substitute that in here. So we have f prime times g plus g prime times f. And that's all multiplied times h of x. And then we have plus h prime of x times m of x. So here's what I replaced with m prime, and then this is what I replaced with m. Now, the last step is to distribute that h of x. So k prime is equal to, I'm going to distribute the h of x times each of these. So I have f prime of x times g of x times h of x plus g prime of x times f of x times h of x plus h prime of x times f of x times g of x. So there we have the derivative of k of x in terms of f of x, g of x, and h of x, like it asked in the question. And even though we didn't know what the actual formula was for each of these functions, I can just write it out using derivative notation. And now we have something we can use for if we have the product of three functions. Okay, in this next example, we are going to work through finding the derivative of h of x, which we will need to use the quotient rule and the product rule. And I think what's going to make this easier is using substitution. So what I'm going to do is I'm going to call the numerator function, I'll call it n of x. The numerator function is 2x to the third times k of x. And I'll call the denominator function d of x, which is 3x plus 2. When I take the derivative of n of x, we have to use the product rule here because I have 2x to the third and times k of x. So I have two functions here. So for the product rule, I take the derivative of the first, which would be 6x squared, multiply it by k of x, plus I take the derivative of k of x and multiply it by 2x to the third. So there's our derivative for n of x. Now let's find our derivative for d of x. If I take the derivative of 3x plus 2, that's going to give me 3. So now let's find the derivative of h of x. And remember, we replaced h of x as n of x over d of x. We wrote that as two separate functions to make this easier using substitution so it doesn't get as messy. So to find the derivative of n of x over d of x, we have to use the quotient rule. So I take the derivative of the top times the bottom minus the derivative of the bottom times the top, and that's all over the function in the denominator squared. So now that we have all the pieces, we just have to plug everything back in and clean it up. So I have h prime of x. So I have h prime of x to be n prime, which we found to be 6x squared times k of x plus k prime of x times 2x to the third. So that's our n prime, and we got to multiply that by d of x, which is 3x plus 2. And we get to subtract the derivative for d of x, which is 3, times n of x, which is 2x cubed k of x. And this is all over, let's see, d of x squared, which is 3x plus 2 squared. Let me try to fix this a little bit. It got really squished in there. So this is 3 times 2x to the third times k of x. Hopefully that's easy enough for you to read. Once you clean this up, you should get that h prime of x is equal to negative 6x to the third times k of x plus 18x to the third times k of x plus 12x squared times k of x plus 6x to the fourth times k prime of x plus 4x to the third k prime of x, and then this is all over 3x plus 2 squared. So the step from here to here, it's not hard, it's just long and tedious, and you just have to take your time and combine like terms. But like I said, I feel like you should be at this point to be able to do that, so I'm not going to go through those steps with you, but just make sure when you go through those steps that you get this answer that I got, and if you don't, let me know and we can go over it in class. Okay, this next example is finding where there are tangent lines that are horizontal tangent lines. And this is going to be a useful skill later on in the semester, so we're kind of wading you in the water here, putting your toes in the water. We'll use this later. So we need to use this function and figure out where there are horizontal tangent lines. And so if I draw just a rough sketch of this graph, it would look something like this, because it's a cubic function. And using my knowledge of degrees and leading coefficients, I have an idea of what the shape of the graph should look like. So the places that we're going to have horizontal tangent lines is going to be whatever that x value is here, because if I look, the tangent line would be horizontal here. And here's another place where we're going to have a horizontal tangent line. So you're basically going to have horizontal tangent lines at your local mins and maxes. So what we need to do, if we know that the slope of the tangent line is 0, what we're looking for is if we take the derivative of the function, and we know that that derivative of the function represents the slope of the tangent line at any point, if I set that derivative equal to 0 and solve for x, that will give me the values of x in which the derivative is equal to 0, meaning where the slope of the tangent line is equal to 0. So we're going to first find the derivative of this function. I'm going to find f prime of x. So when I take the derivative of x to the third, I get 3x squared. When I take the derivative of the minus 7x squared, that's going to give me a minus 14x. And when I take the derivative of 8x, that gives me 8. And when I take the derivative of 1, that's going to give me 0 because that's the derivative of a constant function. So here's my derivative. So I want to find the values of x in which the derivative is 0, and that will tell me where the slope of the tangent line is 0. So I'm going to set this equal to 0. And this will factor. If not, it's a quadratic, so if it doesn't factor, we can use the quadratic formula or complete the square, one of those methods that we learned in college algebra. But this does factor. We can factor it into 3x minus 2 times x minus 4. Now I set each of my factors equal to 0. And I solve for x. For this x, I would get 2/3, and for this x, I would get 4. So if we check the graph at these values of x, I should have a horizontal tangent line. So this point right here should have an x value at 2/3, and this point right here should have an x value of 4. And you can always graph this on your graphing calculator and check to make sure it works. But those are the values where we would have horizontal tangent lines. Now you can do that with any function. You just take the derivative and set it equal to 0. If I wanted to find where the tangent line had a slope of 1, then I would set the derivative to 1 and solve it. The whole idea is just keeping in mind that the derivative represents the slope of the tangent line at any point on the graph. So you can either plug a value of x into the derivative to find the slope at a specific point, or you can work backwards and set the derivative equal to the slope of the tangent line and find the value of x where that happens. Okay, the next example is an application, and it's talking about, given a position function, we want to find the initial velocity of the object. So it gives us the position function, s of t is equal to t over t squared plus 1. Now it doesn't tell us what the units are, but we have to keep in mind that this is a position function, so the units for s of t is going to be like meters or miles or feet or something like that, something with distance. And t is going to be something with time, so seconds, minutes, hours, something like that. Okay, so if we want to figure out what the initial velocity is, to figure out what the velocity is at any point, we need to find the derivative of the position function. So I'm going to find the derivative of the position function, which gives me the velocity. And because this is a quotient, I'm going to use the quotient rule. So I take the derivative of the numerator function, which is 1, times the denominator function, and I subtract the derivative of the denominator function, which is 2t, times the numerator function, and that's all over t squared plus 1 squared. Now, when we clean this up a little bit, I would distribute the negative, combine like terms, all that stuff. We would get 1 minus t squared all over t squared plus 1. But it's asking for the initial velocity. So that means when this object starts to move. So at the instant that it starts to move. So that would be at t equals 0. So it would be 0 minutes or 0 hours or 0 seconds, however the units are measured. So I want to find the initial velocity, which means I want to find the velocity at time 0. So I'm going to plug in 0, and I'm going to get 1 minus 0 squared all over 0 squared plus 1. And that's going to give me a 1 over 1, which is 1. And so since we don't have the units here, I'm just going to put down that this is, I'll just write distance per unit of time. And just write it in terms of generic units so that we know what it represents.